Hello, this is our third guest episode on the standard model with Professor Ananthanarayan of the I- Indian Institute of Science, Bangalore. If you haven't watched the first two episodes, you should watch those first before you watch this one. Professor Ananthanarayan is professor at the Center for High Energy Physics at the Indian Institute of Science, Bangalore, where he has also served as head of the department and guided several PhD students, including at least one of my own former colleagues. He did his BTech at the Indian Institute of Technology, Madras. Switching to physics, he then earned a master's in science and a PhD in physics from the University of Delaware in the US. Anant is a member of the editorial board of the European Physical Journal A and the Indian Journal of Pure and Applied Physics. His research interests are in the field of elementary particle physics and quantum field theory. He works both at the frontiers of the standard model and high precision, and also at finding signatures of interactions that lie beyond the standard model, that is, at finding new physics that can be uncovered at the International Linear Collider. He has also worked on dispersion relations, on the chiral symmetry of the strong interactions, and on grand unified theories and supersymmetric models. Anant is a prolific writer, a popular speaker, and a recipient of the Homi Bhabha Fellowship and the Rustam Choksi Award for Excellence in Science. With that, it gives me great pleasure to invite Professor Ananthanarayan to join us.
Welcome back, Professor Ananthanarayan.
Good morning. Yes.
Yeah. So in the last episode, at the end of the last episode, you talked about the Higgs sector and gluons. Right? I had a couple of questions on that. First is,
yes,
why are the gluons confined? And the second is, what is the meaning of the statement that is often heard that the Higgs gives other particles their mass? So if you can start by addressing those questions, and then we can go on.
Yeah. So as far as the gluons are concerned, it's a phenomenological fact that you never see colored particles. The gluons are constructed in such a way that they necessarily carry both color and anti-color, and this is a result of the properties of the underlying group, which I had mentioned as SU3. So it's not just the gluons that are confined, but the quarks are also confined. So the strong interactions.
You talked about that. You said that as the energy increases, they're more that they feel less
Yes.
force, attractive force,
Yes.
right? Is that also with regard to the distance? So are they confined
So
within
short distance means high energies, just like with a microscope. I mean, you have to think of this as a resolving power of a microscope. You need more and more and more powerful microscopes, by which you mean that the frequency of, let's say, the electromagnetic radiation that is used, the frequency keeps on increasing, the energy keeps on increasing in order for you to probe smaller and smaller lengths. So it is in that sense that there's an inverse relation between the length that is being probed and the energy that is needed for the probe. So in that sense, yes. So at very high energies, which means that as you probe smaller and smaller length scales, then the quarks behave as if they are quasi-free. They are never ever free. They are only quasi-free, and that is why it's given the name asymptotic freedom. So this is a name that was invented by physicists. Physicists are not necessarily the best linguists, but they combine Greek and Latin, they combine mathematical terms with English and so on. So nevertheless, it's an evocative notion that the coupling constant of the strong interaction, it is very large at long distances and very small at small distances. And this is not just fiction. It is all actually measured now in a series of experiments conducted at CERN, at the LEP collider, the Large Electron Positron Collider. They have a very accurate measurement of the behavior of the strong coupling constant as a function of the energy all the way up to this mass of the Z, which I said is 91 GeV. And in fact, the Nobel Prize for Gross, Wilczek, and Politzer, who basically proposed this idea of asymptotic freedom, it had to be validated experimentally because, as you know, the Nobel Prize requires any idea to be kind of established in the laboratory. I'm not saying Nobel Prize is a great thing. I mean, of course, it's a great thing. It's not the only thing, but it's a kind of a touchstone of, let us say, of what mankind considers important at a given
validation.
time.
Yeah.
So that's right. So that's a validation idea. So this was done. So the way in which I went through this was to say that, look, for the Maxwell theory, we just needed one gauge field, one field that provides the force. And then I went on to argue that, look, for the strong interaction, for the weak interactions, for the kinds of transitions that are caused by the weak interactions, you need more than one force carrier. For instance, the neutron that decays into a proton requires that it's an electrically charged one. And I drew a diagram or two to show you what it looks like. Or if I haven't, I will in the future.
Yeah.
So if there is a W plus, then there also has to be a W minus, because nature requires that for every particle there's an antiparticle. And it turns out that these things don't sit on their own. So it's not like they are two copies, W plus, W minus, of each other. They are intimately related, and their properties are intertwined by the underlying SU2 symmetry, which accounts for the weak interaction. And it's not just SU2, but it's a SU2 cross U1, and there's a non-trivial combination of this, which becomes the Z boson, and the orthogonal non-trivial combination becomes the photon. But then, as I mentioned, the behavior is completely different. So why is it that some of these force carriers have become massive?
When you said that the two particles which combine to give the Z0 and the photon, is that like a linear combination of eigenfunctions, or is that something different?
Yes, it's a linear combination of the diagonal generators. The U1 by itself is already diagonal, there's nothing to do. Whereas the SU2 part has two off-diagonal generators and one diagonal generator, which you might call W3. So it's a linear combination of W3 and let's call it the B field of the other U1. One linear combination, the linear combination dictated by a mixing angle called theta. It's called the Weinberg angle, and that was what he did in his 1967 paper, A Theory of Leptons, where he explicitly showed how to mix these things. All these notions today look very similar, but for him to have introduced it at that time is what makes it very remarkable. So this Weinberg angle, it tells you how this W3 and the B mix among each other. Not only that, it also dictates the ratio of the masses of the W and the Z. So that's the thing. This theory hangs together in a nice way that even if you introduce one parameter, it explains more than one property of the whole underlying thing. That's what makes it powerful and economical. That's what makes it the standard model, so to speak. And so that's where we are. So analogously, there's a thing for the gluons, but the gluons, there are 8 of them for SU3, and they carry colors. Let's say RBG, and there is a tensor product with the anticolors R bar, B bar, and G bar. So 3 times 3 will give you 9, but there is one particular combination of this which actually is uninteresting and drops out, and so 9 minus 1 gives you 8, and that's the kind of color anticolor combinations that are carried by the gluons. So that's where we stand. So far, I have only talked about the force carriers that we have somehow introduced, by fiat. So what do these force carriers do, and what kind of phenomena do they produce? What was the other question that you had?
About the Higgs?
And why does it give masses?
Right.
So the Higgs field, without the
What does
Higgs
it mean
field,
by saying that
yeah,
it gives the masses?
without the Higgs field being there, there is no way in which you can write a gauge invariant theory and give masses to the bosons.
So if the
So that was
Higgs
the conundrum.
so if you take out the Higgs field, you would have all these particles without masses.
Yes, that's right. Because well, then you won't have a gauge principle. You can just put in masses, but then there's no symmetry, and then there is no gauge theory, no gauge principle, no nothing.
Okay.
So,
So it's
of course,
integral
in
to
the
the whole
sphere of
thing.
ideas, so in the sphere of ideas or in the sphere of logic, there's nothing wrong with having explicit masses. But then it doesn't account for nature, because today we know Higgs has been found. And in order to make this theory predictive and so on. So that's the whole thing. Nobody tells you what is the basic ideas over here. You have tried many different ideas and some of them have worked. The other thing is about the Higgs giving masses also to the other particles, such as the electron and the muon and so on. And that has to do with this chiral properties of the weak interactions. So you have asked another interesting question. Why is it that without the Higgs, these other particles don't have masses? Because there's another sacrosanct principle, which is that of chirality, the notion that quarks and leptons, they have definite chirality when there are no masses. So the way the weak interactions behave is that they distinguish left from right. Why? Nobody knows. It's the only one of the interactions which distinguishes between left and right. And it is very pure. It says that only left-handed neutrinos interact, right-handed antineutrinos interact. Why? We don't know. This is again phenomenologically known that it is like that. And then if you want to write down terms that represent the interactions of all these particles, then you cannot have an explicit mass term even for the fermions. The only way you can do it is to have a coupling of fermions with the scalar particle. And when the scalar field acquires a vacuum expectation value, which is the notion of spontaneous symmetry breaking, through which the Z and the W got masses, the same spontaneous symmetry breaking phenomenon also gives an effective mass for these fermions. So that's the thing. Why is it like that? We don't know. And the term that you have in the Lagrangian for the interaction is what we call the Yukawa coupling. The original Hideki Yukawa coupling was for a proton, a neutron, and a pion. And the pion was a spin zero pseudoscalar in that case. So we always name interactions of two fermions with a scalar field as a Yukawa coupling in honor of the original idea of Yukawa. So these are not the Yukawa couplings that he introduced, but these are Yukawa couplings for the electroweak standard model, and with Yukawa couplings which are non-zero, whose values are fixed by experiment. There is no theory which tells you what the individual values of these Yukawa couplings are. And when you do that, and this phenomenon of spontaneous symmetry breaking takes place, then the fermions also get a mass. So this is the urban legend of without the Higgs, you cannot have masses. So that is what I have tried to explain in a few words.
Okay. Thank you. And so these the values of these coupling constants and all that, they have to be put in
by experiment.
By experiment, right? So they don't.
So there's no theory.
They don't fall out of the theory itself.
There is no. The theory is incomplete.
Okay,
It's like an engineering model in a sense that theoretically these are all the terms that you add in the Lagrangian which describe the interactions. But actual numerical values of all these coupling constants have to be given by experiment.
I think
so to that extent, the standard.
Even going back to Dirac, that there was an effort to try to explain the values of these of the ratios of the coupling the ratios of various constants.
He had this notion of large numbers and all these things. I think when he got older, and as you know, he was a person who didn't interact much, so he lived in a world of his own ideas, and probably he had this fancy, but there is no basis or justification for many of those beliefs. And Weinberg has given an interview somewhere where he says that this is all mumbo jumbo and listen to these things, and it's only experiment which will tell you. So to that extent, the standard model is really an engineering model. We don't know where the gauge principle comes from, but if you adopt the gauge principle, it gives you constraints. We don't know why there should be Yukawa couplings, but if you introduce Yukawa couplings, then you account for the masses of the fermions. You don't know why the choice of Higgs particle, Higgs fields is what it is, but if you select it in a certain way, it is phenomenologically either ruled out or it is
there.
So all these things are through idea, etc. And that's the reason why we still can only call it the standard model, and it's not.
Okay, I can hear you, but
There's a
the
message that says
video,
unstable network connection. It's okay.
yeah, the
Yeah,
video seems to be
I see.
frozen. Yeah, okay, I think we're
Oh,
back. So this
comes and goes.
old notion of I think Einstein also talked about it, that the Greeks had this idea of that the universe can be derived from pure thought. The structure of the universe can be derived from
Right.
pure thought.
Right.
That doesn't stand scrutiny, as far
That
as we know.
is more in the realm of philosophy rather than in science. But of
Right,
course,
right. Yeah, but as
all
far
the
as we
phases
know,
do meet.
that's not how things are working.
Yes,
Okay.
exactly.
Okay.
Exactly.
Can we get back to your slides?
Yeah.
Yeah.
Yes. I'll start the screen share, and let me share. And you have made my task easy because we have already discussed some of these ideas, and I think I was here until yesterday.
Mhm.
And so let me go on and give you a little bit of zoology of the standard model. What are the particles that it purports to explain, the properties as well as the interactions? So as part of the terminology or the Linnaeus classification of this zoo. So we have these leptons. Leptons, I think, linguistically meant light particles. I don't know why this was used. Anyway, the electron itself, for instance, is a lepton, and it's a charged lepton, and it has a partner, which is an electrically neutral particle, which is the neutrino. And in the old days, there was just the electron and its neutrino. But as people did experiments, they found other charged leptons also, the muon, which was discovered in the 30s. And then there's a third one. That's why it was called tau, tau for three, by Martin Pearl. I think in Slack, he discovered. And they are very similar to each other, except that their masses are different. And then there are their corresponding neutrinos, which you might think is only something experimental, but no, is only theoretical, but no. Experimentally, we know that there are three types of neutrinos, and they have been seen in dedicated experiments. So we'll have to give them a label to distinguish between the three types of neutrinos. They're called nu sub e, nu sub nu, and nu sub tau. So, and they all carry weak charges. All leptons participate in the weak interactions. That is, they all interact with the W and Z boson for sure. They may or may not interact with the photon because if
So
it's
when you say
electrically
they
charged.
carry weak charges, so are the
Yes,
charges
yes.
of two types, like an electromagnetic, plus and minus, or are they
Yes,
more
yes. There are they are like an up and down spinner, if you
up?
like. So one of them
Okay,
will have plus half,
okay. And what are
minus half.
and so these have different charges.
Yeah,
They
they just differ by a sign. So the exact definition, I don't know. Maybe I drew a picture long ago. Let's see over here. Maybe in my early examples. No, it's not here. Later, I have some
okay, okay. We'll come to that.
diagrams
Yeah, and
where I show
and
what
what are
these
the
are.
what are the masses relative to that of the electron?
Yes. Yeah, I have a list of those numbers also. So let me just give you the names of the various animals that we shall encounter,
Okay.
and then I'll tell you which of them is striped and which of them has spots and which of them has, whatever distinguishing features, which of them has horns, which of them has a tail, and so on. So you can think of it as in that way. Then there are also quarks, which
You're
also
giving meaning to
carry
the expression zoo of particles.
exactly. So this
Okay.
really is a zoo. So then there are also other constituents of the other members of the standard model spectrum, as we call it. So here, these are just, this is just a name. Spectrum is the various objects that appear. So just like there are electrons which are electrically charged, all quarks are electrically charged. And in units of the electric charge, they have charges of +2/3 and -1/3. And they all participate in the electroweak interactions. Not only that, the quarks also carry color charges, and therefore they participate in the strong interactions. And as I mentioned earlier, quarks do not exist in isolated color states, and they interact through the exchange of gluons, which carry color and anti-color. And then the theory is so constructed so that the quarks, the colors of the quarks white out amongst themselves. So if you have a quark and an anti-quark, which form mesons, the pions, kaons, there are the particles, which are examples of mesons. The pions are made up of the lightest quarks, U and D quarks. The kaon is made up of one s quark and one of the other lighter quarks. The zeta here is also made up of these three lightest quarks. Then you can also replace, let us say, the strange quark by a charm quark, in which you get, in which case you get charmed mesons, or even heavier cousins of the U, D, S, and C quarks, known as the B quarks, and then you can have B mesons also. So this is a way in which you can easily understand why a quark and an anti-quark can white out. It's a little more complicated when you have three quarks, which is what you need to form baryons. For instance, a proton is a baryon, which is made up of two U-type quarks and one D-type quark. A neutron, on the other hand, is made up of two D-type and one U-type quarks. There are other excitations of protons and neutrons, which are called, say, the delta resonance, where you get the spins of the two up-type and one down-type quark to line up. And then this is exactly like a proton, except that its spin is 3 halves rather than a proton whose spin is 1 half. And this, we just went through your question right now earlier, that the Higgs couples to all the standard model fermions, and through the Yukawa coupling, it gives masses. The Higgs also couples to W bosons, because it's the field that gives masses to the W, so obviously it has to couple. So the physical Higgs that we discovered at the LHC also couples to W pairs. It can also have self-couplings, etc. So now we list the standard model particles.
And when you call
when
you call the higher energy particles as resonances, that seems to suggest that there can be an indefinite number of them by transitions from the interactions with the force carriers and with the lower energy particles, right? Is that?
Yeah, that's correct. So for instance, you can change the spins and get them to line up, and then so that's one way in which you get a resonance. A delta is called a resonance with definite angular momentum. So resonance is associated with having a definite mass, a definite width, and a definite spin. But the forces, for instance, they have to be sufficiently strong. So you can try to radially excite these bound states of quarks also, but then they'll be very unstable and they may never form. Theoretically, it's always possible, but does it really happen in nature? Are the forces strong enough? And all the centrifugal forces and so on may just rip it apart before it even forms. So yes, in theory, you have all these resonances, but to actually produce them and observe them and measure their properties is a different game. Yeah. So today, for the strong interactions, the whole lattice program tries to get all these properties on the computer and trying to understand all these things on the computer. So let me get back to your question and then list all these, in a systematic way. So the idea is that the weak interactions, they would change particle type. You can take an electron and change it into a new type neutrino. You can take a muon and turn it into a mu type neutrino, etc. So the weak interactions through this vertex of a W with a new E and an E is what can turn an electron into a neutrino or cause scattering and so on. So these Ws are responsible for causing transitions between various particle types. So analogously, you can have a W that can change a D quark into U quark, which is the quark level diagram as far as the neutron decay is concerned, because the neutron is made up of 2D and 1 U-type quark. So, for instance, there'll be 2 spectator quarks over here, and then the same 2 spectator quarks, which I have not drawn, will represent the process of a neutron decaying to a proton, an electron, and an antineutrino. And this is the basic decay vertex, which you can read off from the standard electroweak Lagrangian, which is too long to write, so I have not written it. And so this is the transition that takes place with a mean lifetime here of 887 seconds. I want to introduce one more idea, which is the reason why Pice and Freeman actually use this expression and the name standard model. So we have a bunch of interactions where a muon can turn to a new mu and an electron and an antineutrino, and it has a strength or the charge, if you like. This is the charge at this particular vertex is G. So the same thing over here where the cursor is will also have the strength G, and this hypothesis is called universality, which says that it's the same coupling constant of the W with the E and the antineutrino as it is of the muon and the neutrino over here. Okay, so that is the idea of universality of the weak interactions. But it turned out that this was not the case. When the D decayed into a U quark, it was not quite G, but it was a somewhat smaller number, which at the time was called cosine of theta C. Okay, cosine of theta C. So the cosine always lies between -1 and 1. So it's smaller. So this was just denoted by cosine theta C. So if there is a cosine theta C, then there had better be a sine theta C also. And where does that sine theta C show up? It shows up, and today we know this for a fact. This was in the 60s. It was introduced as a hypothesis by Nicolas Cabibot, where he said that, look, this combination G sine theta C should appear in the interaction of an S quark with a U quark, like so. Okay, so that's an interesting thing. So when Pice and Freeman introduced the term standard model, they said it's the electroweak model for leptons as well as quarks, where the mixing between the various quarks, so the D and S type quarks. So this is like a mixing between the D and the S type quark, that he rescued the universality hypothesis and unified both the D and S quarks in this particular way. But then inquiring minds will say that, look, now we know it's not just an S quark, but there may also be a B quark. Sure enough, there's a B quark. So there are all these things, and that was done in a consistent way by Kobayashi and Masakawa. When we say the standard model, it is not just what Pice and here. Yeah. Yes.
I think. Yeah, I can see it.
Hello.
I think it froze a little bit. So earlier you wrote that the D quark and the U quark get interconverted by a W particle, and you have labeled the diagram on the left with the W particle. Now, if the S quark and the U quark get labeled, what is the particle which converts them? What's the particle which converts the S
very
to
good
the
question. So this D. So this is very good. Just like you have a U and D over here, let's write down one more column with a C and an S, a charm quark and an S quark. And then let's take the D and S, and then we rotate them through this angle that we call the Cabibot angle theta C. Okay. So there's more structure. So it's not just a simple transition between U and D quarks, but actually this is a transition between U and a linear combination of the D and S quarks, which is then further extended to the D, the S, and the B quarks. So it's all very interesting, and today we understand these things, but in those days when they were grappling with all these things, it's quite fascinating how they must have come up with all these notions. So I have sent you a picture this morning of the large number of references on WhatsApp. Okay. So there is one book there. It's a popular book called the Second Creation. So this is a good place to read. It's like written like a murder mystery of sorts. about the human aspects in the stories. I have read the first version of this, first edition of this long ago, but I stole this from my colleague's office the other day, the second edition. So when he was looking somewhere else, I just stole it. But so please don't tell him. So there's a large number of books written on the subject, which are all very interesting and which capture all the essence of what we are calling the standard model. So that's what it is. This weak interaction phenomenology is fairly complicated, but if you assume a model and assume a framework, many things get simplified as we go along. Okay.
Yeah, go ahead. We have 10 minutes more.
So even these weak interactions, you can try to understand. They are rather similar to what we already introduced earlier. I had introduced the Dirac-Lagrangian, and then we said that, look, there's an electron which interacts with a photon. And then if you just read it off from the Lagrangian, you will see an IE times gamma mu. These are the Dirac matrices, where the Dirac equation governs the motion of a free Dirac particle, which simultaneously accounts for spin-half electrons and spin-half positrons altogether. So we have an analogous picture here for the weak interactions also. There'll be something like this. There is an interaction vertex. But there's a little more structure here because we said that in life you only get left-handed neutrinos and right-handed antineutrinos. So this gamma mu here is multiplied by a projection operator, which is called 1 minus gamma 5 divided by 2. And gamma 5 is the product of gamma 0, gamma 1, gamma 2, and gamma 3. So these are all properties of the Dirac equation, all well known, all studied about 90 years ago, all these properties. And that particular combination of gamma mu times 1 minus gamma 5
the gamma being the Gelman matrices.
The Dirac matrices.
Oh, the Dirac matrices. Okay.
Yes, the Dirac matrices. Yeah. So let me now complete the story and give you answers to many of the queries that you had a few minutes earlier. So here are the quarks, the U, D, CS, and the TB quarks. So the weak interactions cause transitions not just between D, S, and B, but certain combinations of the D, S, and B. In the case that you didn't have T and B quarks, there would be only one mixing angle. In the event that you have all three families, as they're called, which we do, then there's more structure to this. There's more than one angle, more than one mixing angle. In fact, there are 3 mixing angles. And there is a complex phase that you can never get rid of. The mixing matrix is actually a unitary matrix. It's not the most general of unitary matrices because the physical content of the theory places some constraints on. It's only a restricted class of unitary matrices, which are parameterized by 3 mixing angles and 1 phase. And that phase that you cannot get rid of is very important for a particular effect, which is known as CP violation. C standing for charge conjugation symmetry, and P standing for parity. Thereby, you may also recall, although I have not explicitly written, that the quarks are all colored and carry the colors R, B, and G. These are just names, okay? It could have just been alpha, beta, gamma, or it could have been ka, kha, gha. But the symbols that were used was color because Gelman just simply liked the idea, of calling this color, and he invented the name quantum chromodynamics, chromo as in color. So I guess it's just a name that is stuck. So let's also see, you had asked what are the masses and numbers of these things. So we obviously have to calibrate the scale, and it's good to calibrate it. And let's recall that the mass of a proton is 938 MeV divided by C squared, approximately 1000 MeV, which makes it a GeV. So physicists have their own, scale. You keep hearing of GeV, mass of the Higgs is 125 GeV. It ought to be GeV divided by C squared, but C is equal to 1 anyway. So let's also recall, let's say the ionization potential of hydrogen is 13.6 eV. So that's a kind of typical atomic physics energy. And if you then go to, nuclei, then you may have gamma rays, which are in keV and meV. And in particle physics, we are dealing with GeV. Okay? The mass of the electron here is 0.511 MeV. So this is a famous ratio of about 1800 between the mass of the electron and mass of the proton. The mass of the muon, I already said, about 210 times as heavy as the electron. Therefore, it is 105. And then you have the tau, which is much, much heavier. So it is 1.7 GeV. So it is 20 times as heavy as, not 20, but let's say about 15 times as heavy as the muon, and 15 times, 200 times as heavy. The interesting thing about it, of the tau, is that it is the only lepton which is so heavy that it can actually decay into quarks and other hadronic matter and other strongly interacting particles. The muon can only decay into electrons, probably with the photon in the final state.
Is that
Cannot decay into ions.
Is that 177 or 1777?
1777.0
Okay.
MeV over c squared. Yeah. So it's very heavy. And and the buck seems to stop here. This charged lepton was discovered, let us say, in, I think, 1974 or so. And there have been no other leptons discovered since then. So it just seems to stop at 3 families. So if you asked what are the unsolved problems of the standard model, we have no idea why there are 3 families. Why should that be? Why aren't there 5, 10, 25, 96 families? No idea. It just seems to stop here. Again, it's an engineering aspect that this is the world around us that we are trying to describe. Now, we said that this proton here is 938 MeV, and it's made up of 2 U quarks and 1 D quark. But if you add up the masses of the U quarks, it's very small. So the mass of the proton comes from the strong interactions, from the effective interactions among the quarks. The quarks themselves can, contribute very little mass. They are like very tiny, grape seeds sitting inside, or watermelon seeds sitting inside a watermelon, and it's surrounded by the gas of gluons and QQ bar pairs and so on, which is the red stuff in a watermelon, whereas it may have just 3 seeds in it. And so all that energy is in the form of the red stuff that makes up the watermelon. Okay? And you should not even think about these U quarks and D quarks as being a static seed sitting inside the watermelon, because they're highly relativistic, moving in. These are all unsolved problems. It is just a picture that we are giving, like Thomson gave a model for the nucleus or the atom. Today we have a model for the proton with 3 constituents and a gas of quarks and gluons and so on. But it's only a heuristic description, and we do not know from a theoretical point of view why it is like that. To use another example, just because you know electromagnetism and you know the forces between hydrogen and oxygen atoms, it doesn't mean that you know the properties of water. Water is a collection of a large number of hydrogen and oxygen atoms put together. Some of them have already formed molecules, but still, can you get a property of water? Can you get that at standard temperature and pressure STP? How do you know that the boiling point is 100 Celsius, and how do you know that the freezing is 0 Celsius? How do you know that the density is maximum or at 4 Celsius? How do you know that the dielectric constant is 81? You don't know. Just because you know electrodynamics and you know that the hydrogen atom, you can solve the oxygen atom, you can solve the molecular dynamics, you can solve.
Okay. So you had mentioned that the masses of the up and down quarks don't add up to anywhere close to the mass of the proton or neutron. So it's not like the the constituents of the atom in, let's say, low-lying electronic states, where if you add up the masses of the particles, you get the mass of the atom, more or less. Is that because the rest mass is much greater than the kinetic energy, right? So this is like
These
having a
interactions,
very high
these,
excited state, which would
yes,
correspond
yes,
to in an atom to an unbound state. Is that correct?
yes. Exactly. So that's the point. Because the strong interactions and relativistic field theory, so that's the whole thing. The problem is not really solved. You know, exactly how these things hang together. It's a phenomenological description, where here our normal ideas of just adding up constituent masses, gives the mass of the system. It doesn't work like that, because mass, energy, all these things in the relativistic realm are so interlinked, interlocked, that we cannot really distinguish between energies and masses and so on. So this mass is just a parameter that we use to understand and to fit data and so on. And this confinement is also one of the reasons why it is like that, because the interactions are so strong and so nonlinear. So what does it really mean to have a mass parameter? That's because of confinement. An electron, you can take it very far away from other places where electromagnetic interactions are, and somehow do an experiment there and fix its mass. But since the quark is always sitting inside a hadron, namely a pion or an, or a or a or a or a neutron or a proton, what does it really mean to have the mass of the quark? So these are the various parameters for the light quarks. Especially, it is very difficult to define a mass parameter, because it's highly relativistic when it is sitting inside a pion or a proton. It is less serious a matter as the quarks become heavier. For instance, the charm quark is just sitting inside a charm meson, for instance, is pretty heavy. So there you can have a pretty decent definition of the mass of a charm quark. Even better for a B quark, which is 4.3 GeV. You see, please remember that a proton is itself is a composite object with a mass of about 1 GeV. But then we are saying that we have elementary particles, in contrast to the proton, which is a composite object, which are elementary at 1.2 GeV and at 4.2 GeV. And the biggest anomaly of all is the top quark. Sorry, I wrote this as tau, but this is the top quark, which is the heaviest of all known elementary particles, sitting at 174 GeV. So that is like the mass of, let us say, a gold nucleus or some such thing. I'm not sure there's gold, mercury, something like that. Imagine an elementary particle which is so massive. And because it's so massive and it participates in the weak interactions, it also decays very rapidly. It's one of the few objects which actually doesn't even hedonize. It does not even pick up other quark-quark QQ bar pairs from the vacuum to form a bound state. So when it is produced in some collision, it kind of immediately, not immediately, but with some lifetime, it decays very rapidly long before it gets a chance to become bound. So you see, nature also has provided us all kinds of probes into interactions with all these peculiar properties, different masses, different kinds of interactions, different kinds of final states that they can decay into. The neutrinos also are very mysterious. For a long time, nobody really knew whether they had masses or not. But today, because of some heroic experiments, which I had already mentioned, the Davis experiment, using chlorine atoms, counted the number of solar neutrinos in a certain energy regime predicted by standard solar models, and then it found systematically that there was a shortfall. And today we understand it by requiring electron type neutrinos produced in the sun to have changed their flavor in their during their flight to the Earth, where we carry out terrestrial experiments. And the only way in which neutrinos can flip their flavor from electron type to muon type or to tau type is if neutrinos also have some masses. So we have 3 neutrinos, but only thing measured in the year up till the year 2025 are squares of are differences of masses squared. And these are the numbers that we have. These are very small numbers. Now here you have 174 GeV, whereas here you're looking at masses or mass differences of the order of EV squared, you see. So here you're seeing 9 orders of magnitude. I guess we should really take a square root of this to get an idea of what the mass is. Let's set one of them to 0 and let's take a square root of this. Okay. Then if you did that, you will find that there's a number which is like 10 to the minus 3 eV. So we have like 12 orders of magnitude, not even 12. So this is another 2, 11 plus 3, like 14 orders of magnitude difference in masses of elementary particles. So
So
you
what is
see, so
the
it's not really.
what's the 1, 2, and I3?
Yeah. So there are 3 types of neutrinos. What we know for sure is that the mass difference between the type 1 and type 2 electron and muon type is this. But the other mass difference, we don't know actually what it is. It could be the mass difference between the electron type and the tau type, or it could be between the tau type and the mu type. This is what I understand, that even this we don't know.
Okay.
So the I here stands for it could be either 1 or 2.
Okay.
So there are scenarios where it must be the mass splitting between the muon and the neutrino. There are other scenarios where it is between the electron and the. This is what I understand. I'm not an expert in this. I used to know a bit more, but I've forgotten all these things. So carrying on, so this is also not known. The mass of the W and the Z I have already mentioned is the order of 80 GeV and 91 GeV. Also fixed from experiment. Theory doesn't say what these masses are. It doesn't even say what should be the Sommerfeld fine structure constant. Is just measured to be 1 by 137, whereas the strong coupling constant is of the order of 0.1 at the Z mass. Of course, at very low energies, it's so strong that you no longer have a theory of UCD, but you have effective theories of interactions of neutrinos and of neutrons and protons and pions and so on. So at very low energies, we replace quantum chromodynamics by theory of effective degrees of freedom. The other fundamental constant that's known, which is what enters into the lifetime of the muon and lifetime of the neutron, is what is known as a Fermi constant, which is a combination of the weak charges divided by mw squared. So Fermi was the great pioneer. He's the one who introduced this theory effectively of computing these vertices and trying to predict what the properties of the weak interactions are. Other properties of the weak interaction, which is needed to complete the story of the standard model, if you like, these are things that I already mentioned again and again about parity violation. This was already established in the 1950s by Lee and Young. They proposed it to explain various experimental phenomena, and Lee passed away a couple of years ago, and Young just passed away, I think, a few weeks ago. And parity violation, today we understand it in the standard model, but the structure of that vertex that I mentioned was proposed by Sudarshan and Marshak, what I call gamma mu times 1 minus gamma 5. It has a name called V minus A, because gamma mu transforms like a vector for V. There's gamma mu times gamma 5 transforms under the Lorentz transformation as an axial vector. Therefore, V minus A, and that's why it's called the V minus A theory, which is now subsumed by the standard model. Why is it like this? Nobody knows. We know that it's a fact that it is like that. And I had already mentioned these names: charge conjugation, parity, and time, and the third, discrete symmetry, associated with the special theory of relativity. T is called time reversal. And there's a theorem which says that if special theory of relativity has to hold, then it implies that the laws of any interaction have to be invariant under the combined action of C, P, and T operations: charge conjugation, parity, and time reversal. But it doesn't say anything about any of these separately. One of the consequences of the CPT theorem, which I mentioned, is that the mass of a particle has to be equal to the mass of the antiparticle. Mass of W plus has to be equal to mass of W minus. Mass of the proton has to be equal to the mass of the antiproton. Mass of the electron has to be equal to the mass of the positron. It also says that if you have unstable particles, then the total lifetime of a particle and its antiparticle have to be the same. Although CPT theorem doesn't say anything about individual final states, it only makes a statement about the total lifetime of these particles. All very interesting.
So can you explain that
CP also,
notation?
it turns out.
Can you explain that notation?
Which one?
What is that JP equals 0 minus?
Yeah, yeah. So if we say that we are going to study and if we demand that interactions have definite properties under parity or under charge conjugation, and we also know that particles have a definite mass, definite width, if they are unstable, and definite angular momentum. So pions, for instance, are pseudoscalars. They don't carry any angular momentum, so the J is equal to 0. And under parity, which is spatial reflections, they change sign. So
Okay.
P squared is always equal to identity, which means that the eigenvalue of P acting on any state can be plus or minus 1. Okay? So if it is equal to minus, then it is called a pseudoscalar. So it turns out that the low energy spectrum of QCD, which has pions, kaons, all kinds of particles like this, have very relatively light states with pseudoscalars with Jp equal to 0 minus. Now, this again goes back to another property of the strong interactions and the vacuum of the strong interactions, which is studied by Yoichiro Nambu, who introduced something known as a global symmetry and breakdown, spontaneous breaking of global symmetries, in contrast to the Higgs mechanism, which is spontaneous breaking of gauge or local symmetries. There are so many ideas, notions which go into all these things, but and there are all these breakthrough ideas which, when they were introduced, were greeted with skepticism, but they've all withstood the test of time. So there's a reason why pions and kaons and so on are relatively light and why they become the force carriers of the internucleon force. And this is what was explained by Nambu based on some notions that he had about spontaneous symmetry breaking of the strong interaction ground state. Beyond this, I can't say, but he was also, in a very curious way, he says that he was inspired by the then nascent theory of superconductivity. I think he had gone to Russia and he was hearing some lectures over there, and that's how he tried to, connect the notions that he heard in the context of superconductivity. And he thought that the vacuum state of the strong interactions also behaves like a superconductor. I have no idea how these people made all these connections. It's like a fascinating story. Since you plan to also talk to Dr. Bindu Bamba, maybe you can ask her, because she was a student of Nambu and I think she was fairly close to him and knew a lot about how his mind worked. So it's just an idea. So if CP is violated, and the only interaction that violates CP, not just CNP separately, but the joint combination of CP also, which manifests itself in the decay of certain kaons into final states that are forbidden. Okay? So this, to explain each of these will take another hour, but it's just at least something that I hope that students who are hearing this will just try to pursue on their own to try to understand exactly which combination of neutral kaons and why do they decay, and if they decay in that way, why was it considered forbidden, and by actually doing so, how does it violate C? Okay, so this is again a phenomenon that was first discovered in 1964 in this neutral kaon system, and almost all of it was concluded by the end of the last century, the kaon system. And later, it was also observed in the B meson system, where the S quark that is sitting in the kaon is replaced by a B quark. Interestingly, for Big Bang cosmology, also CP violation is a necessary ingredient, and it goes under the name of the Sakharov conditions. So Andrei Sakharov asked himself if you have a Big Bang cosmology, which was baryon symmetric at the outset, that you had enough matter and antimatter in a very early epoch, how is it that in the present universe you see more matter than you see antimatter? So he studied this and showed that three conditions are needed. That you actually, of course, need to violate baryon number, otherwise you'll never have a net baryon number. Baryon number and lepton number violations, and so that is intuitive, that's obvious. But he also amazingly said that, look, you need CP violation. There's no particular reason why this should have been the case, but he proved that CP violation is needed. Not only that, if you have a buildup of net baryon number compared to net antibaryon number, then if you have thermal equilibrium, then detailed balance will take you back. So you may violate baryon number, but you also have the inverse process going on, and you'll never have a net baryon number. So he also showed that there has to be a third condition, the third Sakharov condition, which is that detailed balance will have to be also violated, and that, or rather, you have to get around detailed balance, and that is achieved if you have a departure from thermal equilibrium. So it's all very, very interesting stuff.
We will stop here for now and continue in the next episode. See you then.